Hey students, I'm going to try another video solution. Hopefully this will help you. Looks like a couple more email questions, really from chapter 2 of the college physics, but the harder problems were over here in the university physics book, and that corresponds to chapter 3. So it's the university physics, it's in chapter 3, it's number 80 here. And this is the book that I use for integrating the calculus into this class. And so let me begin by grabbing a sheet. Maybe I'll kind of fold it here for our discussion. But these are our 5 kinematic equations that I've been illustrating. I used this when I was doing example 53. Let me just cross it out so we won't look at that. But I wanted to start this one by saying, always ask yourself if you have constant acceleration, because then the calculus work is already done and you don't have to do any more calculus. They come out to be these equations, and a lot of our problems are that way. But if it's a non-constant acceleration, we got to go back to just the fundamentals that I'll say the velocity then is the derivative of the position, and the reverse of that is position is the antiderivative of the velocity. And so they undo each other. Likewise, acceleration is the derivative of the velocity, or the velocity is the antiderivative of the acceleration. And so this is the connection, but in general, and if it's constant, well, don't work it out again. That's what I did for you. But if it's non-constant, then, you have to ask, well, how is it, non-constant? What kind of formula does it have? And that's how number 80 comes out to be here. So let's read number 80. Number 80 says this. The velocity of a particle moving along the x-axis varies according to this equation. Velocity equals a plus b multiplied by t to the negative 1. Or maybe you would write it as a plus b over t. So there's our equation for velocity. Then they go on to say where a has a value of 2, b has a value of 0.25, so that's a quarter. And then it says, and the time t is any time that is greater than 1 second, but less than 8 seconds. So this equation is only valid in a window of time. And you can kind of see why they didn't allow 0 time, because obviously dividing by 0 would be problematic. So this number seems, as time gets bigger, this gets smaller. Okay. And so you're taking a, which is 2, and you're adding, as time increases, a smaller and smaller number. So your velocity changes according to that equation. Maybe I'll box the equation. But like I said, all of these questions, you need to start off by asking a simple question, is the acceleration a constant? And sometimes they tell you directly, sometimes it's even just maybe indirect, but pretty straightforward. They'll just say a is 7, and so they mean it's always 7. Here, though, I would say maybe it's a little harder because they have not given me an equation for acceleration, and so you might be asking yourself, is this a constant acceleration problem? Because again, if it is, I'm going to use this. If it's not, I'll go back to doing the integrations. I suppose, if you don't know, this is good all the time, constant acceleration or not. It's just, why do these again if you have constant acceleration? Because we work these out. Now, I would answer it this way. Since we already worked out the formulas for constant acceleration, see what it says here? It says that if you do have constant acceleration, the velocity is, and we would call linear with time, raised to a power of 1. What we have is something different than that. We have raised to a power of -1. Basically, if it is not this equation for velocity, it would not be constant acceleration. I mean, this is the set of equations we get when you have constant acceleration. So if they were to give you a formula that looks anything different than this, and so what we'd call a straight line, linear, and this is not a straight line. This is not linear. This is not raised to a power of 1. This is raised to a power of -1. So anytime time would be raised to like 1/2, or -1, or -7, or raised to a power of 7, raised to a power of 2. As long as it's not raised to a power of 1, it doesn't fit this pattern, and it wouldn't be constant acceleration. So that answers my question. Is it? No. And so I do not have constant acceleration. All right, so that's important to notice, noting that I can't use any of these. So let's push this off to the side, tell another problem. Not going to use that. My question, then, is it says determine the acceleration. Okay, so I want to find the acceleration. And so to get the acceleration, you take the derivative of the velocity. Okay, so acceleration equals derivative of, and let me just put in that equation, a plus b to the -1. Okay, so this is a nice calculus review. That would be the derivative of the first term added to the derivative of the second term. Now, what is the derivative of a constant? Well, that's 0, if you can remember from your calculus class. And so remembering derivatives of constants are 0. Also, remembering that constant values can be pulled out in front of derivatives as well as antiderivatives. You guys, I think, saw me do that in class a number of times where I pulled out in those examples a constant doing the antiderivative. I'm going to do that here with the derivative. Oh, why'd I put a b there? T to the -1, okay. And so now I'm taking the derivative of a power function, right here. And when you take the derivative of a power function, maybe I'll just kind of remind you, I'll put it up here. The derivative of a power function, you probably learned it this way, that if you take the derivative, say, of x, when you have x to the nth, you bring the n down in front, so it comes a prefactor, and then you reduce by 1. Just like the antiderivative we talked about, you increase the exponents by 1 and divide by the new exponent. So that's our basic calculus that we need, taking derivatives and antiderivatives of power functions. So now I'm going to take a derivative of this power function. So bringing the coefficient down, that would be a -1. And then reducing the exponent by 1. So it's already -1, so that's going to become a -2. And maybe simplifying it, I'll put the negative in front of the b, and I'll put the 2 downstairs. And so here would be the equation. I suppose I can do one more step because they did tell me the value of b. And so 0.025 over t squared equals a. Okay, so there's the mathematical equation that they're asking for. What's the acceleration? And likewise, they are asking for position. So it says determine the position of the particle. And then they give some times. So I'll plug in the times here in just a second. But let me just get the general equation, and that comes back to this statement here when we got started on this problem, that to get position, you take the antiderivative of the velocity. Okay. So I am going to integrate, that is the antiderivative of the velocity. The velocity is a plus b t to the -1 dt. And so that would be an integral of the first term plus a integral or antiderivative of the next term. Ooh. Ooh. Ha ha ha. Okay. Okay. I just realized that this is a little harder than it first looked, because this statement I made earlier about how to take an antiderivative is true except when n equals -1. See, if n equals -1, you would have -1 plus 1, which puts a 0 in the bottom. So this is a problem. And without proof, I'm sure you did it in your calculus class, the power function for x to the -1 becomes the natural log of x. And so that one exception we've got to think about separately, which this one probably gave you a real headache in your calculus, because it's the exception, and proving it is quite challenging. So I'm not going to try to prove it to you. I'm just going to point it out that that's the exceptional rule, and I forgot about it for a moment until I ran into it right here. So this is going to be a little annoying here. Okay. All right. So with that in mind, let me go ahead and do this integral. So this would be an a, it's a constant, I can pull it out. And then you can think of that in here as t raised to the 0 power, because t to the 0 is just a 1. And so if you don't have anything in there, you just have the integral of dt. So coming up to our little rule here, we would add 1, so this would become a t to the 1, and technically you would divide by 1. And this integral would be a b, but being raised to a -1, this is our exception, and so this becomes a natural log of t. That's an interesting one. So this is a little harder than I anticipated when I assigned it. I didn't really want to focus on the kind of the exceptional ones from your calculus class. But let me also point out that when you do an integration, there is some kind of constant. I suppose technically you would say there's a constant for each one, but I would just, in my mind, if you will, add those two constants, and then that is just some other unknown constant. So I'm just going to think of it as one constant that has come from the sum of two other constants, but I might want to take a moment to kind of look to see if this is useful. And it is, because let me read the problem in greater detail. It says, determine the acceleration and the position of the particle at 2 seconds and at 5 seconds, and assume that the position at 1 second is equal to 0. And it's that last part that gives us some information to get this constant. So if you put in the value of a, which we said was a 2, and then you put in what they say at time equal 1 second, put in the value of b, which they write as 0.25, and at 1 second. You can then figure out this constant, because they say go ahead and assume that at 1 second, so I put in 1, the position is 0. And so now we can actually get this constant. So 0 equals, and obviously 2 times 1 is a 2. This one might be a little harder. The natural log of 1 is 0. And so there's our answer to what this constant is. When I move it over, negative 2 is the value of that constant. So antiderivatives are always a little bit harder than derivatives. Most calculus classes start then with derivatives and then move into antiderivatives for just that reason. Although I think conceptually antiderivatives are kind of a nice place to start, but their math is a little bit harder. So there's a few calculus classes that start with antiderivatives, but it's kind of weird starting with the antiderivative. So I suspect most of you did the derivative first. But let me finish this by then saying I have the equation because it would be a times t, so that's 2t, plus 0.25 natural log of t, plus the negative 2. Why don't I just say negative 2 like that? So this here is the equation for position, and as we did earlier, this is the equation for the acceleration. So when they ask for what is the acceleration at 2 seconds, I can put a as a function of t, so that's 2 seconds. I would have right here negative 0.25 divided by 2 squared, and so that's 1/4. So I have 1/4 of 1/4, so that's 1/16. Maybe I'll do it as a decimal. So 1 divided by 16. So 0.0625, and let me not forget the negative. So that's the acceleration at 2 seconds. The other one would say, what's the acceleration at 5 seconds? Okay. So I will go negative 0.25 divided by 5 squared. So it's a quarter, 25. Oh, well, it's 100th. And so that's 100th. And so that's a negative 0.01. Okay. And so those are the easier step. What is the acceleration? And the hard one, and this is probably why then I got this question, is this integral with the constant comes out to be this. All right, so position then, and I'll just do it 2 seconds, would be the 2 times the 2 seconds plus the 1/4 times the natural log of 2 minus a 2. Okay. And so I will have 2 times 2, that's a 4, plus a quarter times a, what's my natural log? Natural log of 2, and then subtract a 2, and we are looking at a position of 2.17. So apparently, between this 1 second, where it's at position 0, and this 2 seconds, it's moved over from 0 to 2.17, according to this math. And if we do it again, and say, all right, what is the position at 5 seconds? Okay, we can put in the 2 times the 5. So I'll just put the equation here in the screen. So here it is, 2 times 5 plus 0.25 times the natural log of 5 minus 2. Grabbing a calculator, 2 times 5 is 10. Add to it a quarter times the natural log of 5 and subtract a 2. And so now it looks like it's at 8.7. for 0 after 5 seconds. So that was interesting and a little harder. So hopefully that was helpful and a bit challenging here. All right, that's a good one. All right, take care.